So today I'm going to tell you about Harry Potter, Invisible Cloak, Star Trek, and so on. And I am from the physics department. Yeah. And so this is, I'm not blocking. This is Mr. I have to apologize for that side because the geometry room I probably cannot point to that side, so I can point to this side. So this Mr. Harry Potter, and he has this magical cloak. I can make him invisible. And you may also know that this is the so-called platform 9 3/4 that Mr. Potter used to go to his school. And this platform is there, but it's also not there. Okay, so but it's there, but you can just go through it. So it's kind of illusion. And of course, for some of us who have seen Star Trek, they have this wonderful technology. Image, if you want to fetch something, for example, if I want to fetch the microphone there, I don't need to go there, I just need to point a laser and then I can direct it there. Now, but of course, for those of us who still remember our high school physics, this is total nonsense because we all know that photons, light, can only push it in a pool. And these are all just magic, okay? And so these are not supposed to be possible in real life. But of course, these are basically artist conception. And in movies and fiction, it's only bound by the imagination of the author. But in real life, we have to be bound by the laws of science. So the question is it really impossible, or is there any possibility of realizing some of these rather wonderful, maybe far-fetched phenomena? And in fact, the science community would have regarded things like invisibility or attractive beams as something that is against the laws of nature just a couple of years ago. But I'm going to show you today that some recent research work, including some of the work done in our university, show that in fact some of these are possible. And while these, I'll be honest with you, are academic exercises, but these can be the foundation. Some of these may be able to have an impact in the near future. And so, but of course, these things are really, really on the fringe, really on the far side in a way. So, in order to make these things possible, we really have to think of the box. And I don't want to be too philosophical, but just for some great writers say, the great pressure in life is doing what people say that we cannot do. This is something that we try to achieve. And also, this is a very famous science fiction writer. He's the guy who wrote the script for the 201 Space Odyssey, Arthur C. Clarke. And he said something which I think is very meaningful. I just want to repeat to you. He said that when a distinguished but elderly scientist says that something cannot be done, something can be done, he's probably right. But when he says something is impossible, it's very probably wrong. And the only way to discover the limits of the possible is to venture a little bit past into the impossible. And any sufficiently advanced technology is indissoluble from magic. So I'm going to show you that something that's thought to be impossible can be done, and it's not so far away from magic. Now, so I'm going to talk about invisibility today, but I want to distinguish between two different concepts, which can be very confusing for people who use the Chinese language, because in the Chinese language, we call invisibility 人形, stealth also 人形. But these two terms have totally different meaning. Okay. And these are a couple of war machines. This is the F-117. This is Solar Street Shadow. This is a warship for the Swedish Navy. These are all what we call stealth. By stealth, I mean that this is something that cannot be detected by radar. Now, let me show you why it is the case. Now, first of all of these war machines are coated with a layer of radar-absorbing material. And imagine that this is a Harpoon missile or the exocet missile that is coming to attack this US Navy ship. So the missile comes in, and the missile have, in fact, in the tip of the missile is that there is an active radar. Okay, it sends up a beam of radar, and it hits the ship, and it can bounce back, get reflected, and there is also a receiver on the missile tube, and when we sense the reflection, then the missile knows the location of the target, and then it will go to the target and destroy the target. And so the reason that the radar or an active weapon works is that they have to send something to you, and you reflect that signal back to the receiver inside the missile before the missile can, as an active seeker, to attack you. Now, and the fact that these things are coated with a layer of absorbing material would greatly diminish the reflecting signal. And if the signal is overwhelmed by the noise, the radar in the missile will be confused. And more importantly, you know that all these have these angled surfaces. And it has one very important function. Suppose that my missile is coming in, and my beam of light is coming in here. If this is a vertical surface, suppose that light comes in, it will get reflected back to you. But if it's an angle, so all these have these angled surfaces. It gets reflected to the sky. And therefore, the receiver at the missile cannot receive the signal back to you. And therefore, the missiles do not know where is the target. And this is called stealth. Stealth simply means an object that when you send an active radar source to it, that signal do not go back to the source. This is called stealth. Now this is not invisible, because I can very easily teach this technology. For example, if I don't have one single missile, but suppose that I have two sources. Suppose that I have an airplane that has an active radar. It also shines a signal into it. The scattering of that radar will be affected by these two all angles, and my detector will be able to detect it. Okay, so stealth is no way invisible. Okay, it's very far away from invisibility. Now, what we mean by invisibility is more like something in the movies and the fictions. And for example, this is an invisible lady and invisible man. In fact, invisible by scientific terms means something that is totally transparent. Light just go through it as if it's not there. And so this is a movie in the 80s. Okay, so you have this alien that is hunting around, and he can push a button and make himself basically transparent, and therefore he has an advantage over his targets. This is what we mean by invisibility. It's not the same as stealth. Now, invisibility, of course, has been the subject of fantasy for ages. And I think this may be quite a famous book by H.G. Wells called The Invisible Man. Now, in the 19th century, people who are thinking about or dreaming about invisibility always think that you can do so by making a cocktail. So we have to come to some chemist, for example, our distinguished colleague, Reinberg is there. So Reinberg may mix a cocktail for you that you drink it, and then suddenly after some internal, whatever, combination of molecules make you totally transparent. This is actually not a very good idea. The reason being that if you want to transform yourself into totally transparent, it must be a very drastic chemical change. And it's probably not good for your health, and it is probably you can only do it once. And even if you can do it once, it is not a very good way of doing things. Imagine that you can drink something and make yourself as an organic material transparent. Only you become transparent. Your clothes are not transparent. So you have to take off everything before you can be really invisible. And that is certainly not something you want to do, especially in the winter time. Okay? So now, but in the 20th century, the writers become a little bit more realistic, and they think that it's not a good idea to transform yourself to make yourself transparent. So instead of changing yourself, you change your environment. So this is in fact much smarter. So thinkers do change and do become smarter as time goes on. So almost you see that for all 20th century fictions, TV series, movies, they all think of making something totally transparent, invisible, by not changing yourself, but by changing your environment. Including, for example, this is Mr. Porter again, he wears a cloak. Okay? This is Star Trek technology, don't know how he did it, but push a button, it becomes transparent, and again for this alien technology. Now, but of course all these are just fiction. Okay? No, but amazingly, in the year 2006, there were some British scientists who actually did some mathematics. Now this is entirely technical stuff, so I only advise me don't do anything technical, so I won't bore you with the details. But basically, what they have succeeded in proving is that there are some material in which, if you can make them, okay, you can use it to surround a certain object. And then this material has some very special properties that when light comes in, it will be guided around that object and then go back to its original path. So that for any observer standing there, he will have the illusion that in fact light comes straight through that object, and therefore anything hidden there would not be detectable by anyone outside this cloak. And this cloak is called the invisibility cloak. Now in fact this was of course a scientific paper, but after this paper was published, it was almost instantly caught the attention of the media, and so it was reported by BBC and so on and so forth, Scientific American. And this is a simulation done by ourselves. This is not a cartoon, it's really a numerical simulation, assuming that we do have the recipe to create or make the fabricated material suggested by these spiritual scientists. And then you can see that when light is away, comes in, and it just simply go around the object as if nothing is there. So anything sitting inside would not be able to, you will see them. Now, but however, while this is really a fantastic idea, and trust me that the physics and the math behind is exceedingly difficult. So it's only probably, at least initially, only a handful of people understand what is behind it. But I can assure you that this is correct physics. Okay. But however, if you use this type of technology to make something invisible, you do have a problem. Now, if I may go back to previous slide, look at this Mr. Harry Potter. Now, supposing that he has this cloak that also covers his head, then you will not be able to see him. Now, in fact, I did see that movie because in that movie he really used the cloak to enclose himself entirely. So when he go into the library, other people cannot see him, but he can see other people. And if you want to have an advantage over your enemy, you have an advantage only if your enemy cannot see you, but you can see the enemy. Now, but imagine that this British way of doing cloaking. They do cloaking basically by guiding light around your object so that light would not enter that object, and therefore you don't see the object. And therefore, if you put a Mr. Harry Potter there, you won't see that Mr. Harry Potter. But since no light or no information can enter that space, that Mr. Harry Potter is totally blind. You don't see him, but he sees nothing. So instead of having an advantage, this way of doing invisibility, in fact, put Mr. Harry Potter in not in such a good position because you can't see him, but at least you can see the surrounding, but he is totally blind. So imagine that you want to make a warship invisible, then your enemy cannot see you, but you cannot see anyone, and therefore that kind of war machine is probably not very useful. So therefore, when we saw that paper, then we think of, so we pose a problem to my group. You see, can we have a device so that without that device, this object, it may be you, it may be an airplane, or maybe a ship, whatever, will scatter light, and therefore other people can see that object. Okay? Can I make a device, a cloaking device, so that it can cancel all the scattering of this object, so that the whole thing here looks like just a volume of air, so that an observer will see nothing. Now, if it is the case, then this is not enclosed. I want to insist that this device I'm thinking about do not enclose this object in the cloak, and therefore they just sit next to each other, and therefore it will not the outside view will not be obscured, and therefore you can't see him, but he can see you. Okay. And without going into details, I'll just show you some results that we have. On the left-hand side, I'm showing that I have an object there, and light as a wave comes in, and this object is visible because it scatters the incoming wave. The same way as you can see the screen here because it is reflecting, scattering the light from the projector. Now, this is the device we have designed, and again, this is not a cartoon. This is putting in real material there, doing a simulation, and you can see that before I put so-called this cloaking device in, then wave gets scattered. And by scattering the light, you're disturbing the field, and therefore you know that there is something there. Now, by putting this thing in, all the scattering got compensated, and therefore the wave simply just passed through as if nothing is there, and therefore for someone sitting there, you will not be able to tell whether there's something there or there's nothing there. If there's nothing there, wave simply just pass through as a thing like that. And therefore, by doing so, we found a way that I can make this object invisible as compared with this one. But however, the important difference between what we do here and what the other people do is that the wave is entering this object, and therefore if you have eyes or detectors inside, you know what's going on outside. And therefore, if I use this device to make this object invisible, this object would have an advantage over the observer outside. You can't see him, but he can see you. Okay, so this is something that we call remote cloaking. If you might pardon me, I'll take off my jacket.
Now you're visible.
So now I become visible to you. Now after that, then I thought about, can we take it one step further? Now, if I can put something, to make an object invisible, now can I actually, in scientific terms, if I put something here to make something invisible, what I'm doing is that I'm putting in A plus a B, I want the whole thing equals to just air. Okay, air is transparent. So if I say that I can make something A plus B equals to air, can I make something A plus B equal to C? Now, to put in plain English, what I mean is that I have an apple here, and therefore you say an apple. Can I put something next to an apple to make it look like a banana? Okay. Now, all we talk about invisibility is basically by enclosing something or putting something next to an apple to make it look like air. This is what we mean by invisibility. So the question I pose is that, can I put something next to an apple to make it look like a banana? Okay. And if I can, then I'll be able to create an illusion. And probably I can skip this one because talking about it, maybe very quickly. So basically, the technical specification is that I want to have an object here. I want to put another piece of instrument here, and I want that when this is placed close to that one, then when the light or radar comes in, then the scattering becomes the same as some other. Can it be done again for the simulation? So my intention here is to make a spoon look like a cup. Now, on my left-hand side, I show that I have a spoon. And when light or wave comes in, the spoon scatters like a spoon, and therefore you see a spoon, okay? And the spoon here leaves a shadow there. Okay? Now, on my right-hand side, I have a cup. Because the cup has a different shape compared with the spoon, and therefore the light being scattered is different. Now, in particular, you know that I have some flat surfaces here, and then wave comes in here, I have refractions here, and this angle has refraction, and also a shadow. And so that when you see a spoon or a cup, you see different objects, mainly because different objects, because of the different shape and geometry, they scatter light and wave in a different way, and therefore you see different objects, you interpret them as different objects. Now, what I'm showing you on this middle panel is that I can design a device in which when it is pushed near the spoon. Now, you see that this is the spoon alone. Looks like a spoon. Okay. If I put this together with that one, you will see that the way that these two objects together scattered, in fact, look pretty much like a cup here. And therefore, by using this device, I would be able to turn a spoon into a cup. And therefore, this is of course a numerical simulation. But what I mean is that if I put a spoon there, I should be able to design for you some material, and I put it together with this one. For you standing at a distance away, you will see a cup instead of a spoon. So it can be done. Now, this is just part of our work, and other things that we have been doing is that, for example, can I make something which is more empty than vacuum? Now, for most of us, we think that vacuum is the most empty thing you can think of. And vacuum means nothing. Okay, but for physicists, vacuum is actually not exactly nothing. One good evidence is that our sun is very far away from us, and in between us and Earth and the sun, there is a big distance. Light, in fact, takes 8 minutes to come from sun to Earth. And for this 8 minutes, in fact, it's traveling through vacuum. And therefore, vacuum is not entirely nothing, because at least something can go through that, right? So my question is, can I make something that is even emptier than vacuum, as far as light is concerned? And the concept behind requires a lot of math, so probably I don't want to do it. I just want to show you. The real social is that because all I'm talking about theory, we're talking about calculations, something that can be done in principle. This one, we can actually, the system is simple enough that we can afford to do an experiment, okay? And I just want to show you that we have designed something that is more empty than vacuum. Now, what can it do for us? And now, for example, if I have a certain region of space in which I put an object in, this is a piece of metal. Now, this is not a simulation, it's a real experiment being done. And so I shined microwave in, and this microwave will be about the same frequency as people use in radar. Okay? And this object leaves a shadow. Okay? Now, I can design something which is more empty than vacuum. I won't empty in vacuum, meaning that this space doesn't exist. And if I embed something in a space that doesn't exist, you won't know that it is there. And this is, again, not a simulation. It's really experiment being done. So now, instead of leaving it to just air, I surround this object by a material which we call a zero refractive index. Okay? Because light have a refractive index of 1, and we have a material that can reduce the index to 0. Now, this technically means that I basically murder away this amount of space. So this space does not exist as far as wave is concerned, and therefore we just tunnel through. Okay? And therefore, it is a way also to hide something. Okay, you put something there, you won't see it. Okay, so it's another way to achieve what we call invisibility. And this is again, emphasizing this is experiment being done. Okay, and no, but at this point, I do want to manage your expectation because Mr. Ma said that we should think about commercialization. Now there is this. My understanding is a free lunch, but in science there's really no free lunch. If you want to do something that can achieve something that's quite amazing, then you always require something that is amazingly complex. Now it turns out that for all the material that I have said, why don't I come up with a demonstration kit to show you that I can make, for example, totally invisible. And the problem is that none of these materials that we can design exist in nature. Nature does not provide us with something like this. Nature does not want anything to be invisible. If we want to do something amazing, we need to make these materials in our own laboratory. And these materials are amazingly difficult to make. And they are also ultra expensive to make. And these are some of these things made in the laboratories in the United States and Europe. And they typically would require some what we call artificial atoms that are very much smaller than a wavelength. And so we really need to go to nanotechnology and to make these very funny structures before they can achieve what we want to do. So all we can do here in Hong Kong is to design those materials. And to make this is extremely difficult. Okay? And how small are these? And these are smaller than a micron. And so the feature size of it would be like 1,000 times smaller than a micron. So it's sitting, and these are multi-layers and very different layers, and each one is different. So it is very difficult to make those things. And I just want to show you that colleagues in Hong Kong, I'm famous, but there are some experimentalists who are also trying to make these materials, but they are awfully difficult to do. Now, another thing that, as I've said, that in the Star Trek, this is of course it's Captain Kirk, Mr. Spock. Now, in science movies, it's always the case that scientific officer is always the second in command. Okay? And basically for good reason for that. Okay. And of course, they have this technology that can use a beam called attractive beam to attract something from a distance. Now, this is certainly, if you go to high school, and if a high school student say that it can be done, he will definitely fail in his physics courses. All the physics textbooks tells us that light can only push, it can never pull. Okay. But however, I cannot, because this is really difficult, because they really do not have a way to make it simple. But I just want to show you that last year, my student and I found a way that technically speaking, it is possible, okay, to use light to attract, but you need some very advanced techniques to create a special kind of laser beam before you can do that. But the details would not be easy to say in about a few minutes, so I will skip that. But just want to show you that it can be done. Okay. Now, I just want to show you that, of course, only pay us to do good science, and we do. And in fact, the work in Hong Kong is not just being published in journals, has been reported by a lot of magazines, Nature Science, and Discovery Channel, and Scientific American, etc. They have reported our work here. And of course, I think the town, when you meet the gang, would like to know, then so what? Okay, after all these science, what can it do for mankind? And these things, in fact, can be quite useful. Now, for example, you say, why would I care to make something invisible? And let me just fox backward a little bit. And for example, let me just show you one. For example, if I can do something like this, then who cares? Maybe for the military, it may be useful for them, but this is not the mandate of the university to solve military problem. It's somebody else's concern. But imagine that you are sitting there. What it does for you is, in fact, it creates a region of say, you call it quiet zone. This is a zone that's not disturbed by the wave. You say that, why do I want to be not disturbed? And for very good reasons. For example, if you think that this is too noisy, you want some privacy, this can do for you. And imagine that this is some electromagnetic wave that you do not want. Okay, you want to be shielded from some wave that you do not want. It can be done for you. And what if this is earthquake and coming in, and this region is protected? Now, even I myself would thought that this is too far-fetched to shield an area from earthquake. I just learned last week when I invited a couple of experts to Hong Kong, and one of them is already doing this for the European community, that they're really designing something that can shield a region from earthquake. Then I talked to that scientist, I say, but we all know, being scientists, that it will take literally multi-million, maybe $1 billion to build this thing to protect the region, because it's extremely expensive to do this thing. But he said that, yes, it is very expensive and difficult to do. But he said that if you do something on the boundary, and if you can protect an area, then that boundary can be expensive, as long as that asset inside is worth protecting. And he imagined that suppose that this asset is not just a single house, but in fact a tall building. He said that if you want to make a tall building that can withstand a Richter scale age, then the material inside is very expensive. But if you can protect it with a ring, and the ring can be expensive as long as, because you're talking about just a line, a boundary. If that expensive boundary can protect a volume, then the mathematics become a different thing. But of course, if what is sitting there inside is, say, a professor of physics, then of course nobody cares. But imagine that it is a president of the university, or maybe the managing director of a big company, then maybe it's worth doing things. So, let me quickly go. But of course, there are many other things that can be done. For example, using light to attract something is a way to, in fact, manipulate small, tiny particles, because light is, in fact, the most non-contaminating things to manipulate things. And these things can also be used to make lenses and so on, and they have their own advantage, which I don't have time to explain to you why. And also, these things can be used to design good absorbers, okay? And for example, for solar photovoltaic harvesting, you want to protect against noise in the environment. And these things can be used to do what we call high sensitive sensors. And so there are a lot of things that you can think about. And of course, you say that after this, what next? And of course, in order to make these things practical, basically what we have done is that we have found some solution to some problem. But these solutions are amazingly complex. So the next step to do is that, well, we know that some problems, for example, can make something invisible. Now we saw that there exists one solution. But usually a problem, the solutions can be more than one. So the next task, which can be in fact more difficult, is that is there an easier solution to a complex problem? So what we now found is that we found a complex solution to a complex problem. So making something that is supposed to be impossible is now possible, but it's still very difficult. Can I make something that is easier to do? Okay. Or are there better ways to make these extremely complex materials? This is something that we want to explore in the future. And of course, university is very nice, but just in fact, not too long ago, approved setting up a center for material research to carry on this kind of research. And we have a plan here. Of course, initially we want to do more theory, do more design, and then next step want to make them. And of course, in maybe 3 and 5 years, we want to make something that is useful to someone. And but at the moment, the funding for the center is exactly zero. So for the moment, so we are still with no money, but you can still think, okay. But to make it one step further, maybe we need some funding, and this I'm looking forward to some interaction maybe that can make this possible. And with that, I thank you very much for your attention.